Hello, my name is Hang Ha Pham, belong to team 190. Today, I would like to present our project, namely Data Visualization, Ukraine Air Quality Index Forecasting. First of all, I would like to talk about the project background. As you know, climate change is impacting weather patterns, making it imperative to adapt our daily routines. Nowadays, developed countries can create complex weather models. However, many less developed nations like Ukraine lack the necessary infrastructure. Our literature review show that underdeveloped countries are often unable to access the resources needed for accurate weather predictions. Even as they face the most severe consequences of climate. Advanced models may deliver high accuracy, of course, but they require significant computational power and typically prioritize performance over interpretability. It's time to change that narrative and emphasize visualization as the key solution. For these reasons, our goal is to develop low-cost, efficient, and interpretable ARIMAX model that emphasizes a generalized measure of air quality, specifically the air quality index, one of the Europe standards to communicate the quality of outdoor air and its potential health effects. Before going through the detailed method, I'd like to introduce about ARIMAX forecasting model. ARIMAX stands for Autoregressive Integrated Moving Average with Exogenous Input. It is an extension of the ARIMA model. We use this model on pooled data and then deploy individually across 28 monitoring weather stations. Two primary targets of the forecast were PM2.5 and PM10 concentration levels. Now we will deep dive the data analysis. Firstly, we conducted data preprocessing included time normalization and imputation of missing values. The cleaned data consisted of 20-minute interval measurements of PM2.5 and PM10 from the monitoring station. Historical data was used for training, while the most recent observations were reserved for model validation. Each ARIMAX model integrates a range of engineered features, including up to 12 lag variables to capture temporal patterns. We apply exponentially weighted moving average to make prediction smoother and more robust. We also calculated lag differences to show the change from past to present. This feature helped with trends and stationary. The slight random noise were also added to training dataset to prevent overfitting and promote generalization. To address the skew distribution and stabilize variance in the data, a log transformation was also used in our data analysis. Forecasting was conducted in 30-step patches, which means that we predicted 12 hours ahead in one go. Notably, we didn't feed predicted value back into model during forecasting. Why? Because we want to avoid error accumulation and keep output stable. Furthermore, to manage volatility, prediction volatility, regularization and smoothing techniques were applied to the forecast output. The results of the forecasting process were were illustrated through the dynamic visualization in Tableau, showing the platform's advanced capabilities. Now I will show you our Tableau dashboard. This is the visualization display the result of forecasting process. We display pollution concentrations in 24-hour intervals. This section highlighted both actual and predicted value using calculated view in Tableau. Parameter control here allow user to switch between different pollution indicator. I will show you. Next, in the second visualization, predicted value was translated into air quality index score here, right here, to further enhance interpretability. This score were then displayed using gray chart, providing user with a clear and immediate understanding of air quality levels. We have 5 air quality right here: good, fair, moderate, poor, and very poor. The last visualization was about geographic the last visualization was about geographic pollution assessment. Tableau helped us map this location using latitude and longitude. We assess pollutant concentration levels in various locations using color markers and uh, color marker, and user can explore pollution level at each location over time with slider right here and interactive filter right here. I will show you how everything changed. You can see the location change based on the concentration level in various locations, and the air quality index performance change accordingly. Okay, now we will get back the poster. Let me get back the poster. Regarding evaluations, in our project, we conducted a series of experiments aimed at optimizing time series forecasting for air quality predictions. Firstly, a comparison between 12 hours and 24-hour training revealed that the 24 hours window reduced the root mean square error from approximately 100% to 121%. 150% to 121%, suggesting that a broader temporal view helps stabilize the ARIMAX model's prediction and better capture pollution dynamics. Secondly, the inclusion of exponential weighted moving average figures, especially in regions with high variance due to industrial activity, contributed to smoother and more consistent recursive forecasts, mitigating the typical noise accumulation seen in multi-step prediction. We also leverage Google Cloud's parallel processing that significantly improve computational efficiency. Training and forecasting time will reduce from approximately to 5 hours to just 20 minutes. That's impressive. About the conclusion. In conclusion, our findings emphasize the importance of carefully chosen modeling strategies, such as extended training windows, exponential moving average integration, and computational scalability in improving the reliability and usability of air quality forecasts. The approach demonstrated support a real-time environmental management system. However, our project does have some limitations. Initially, we planned to create a separate model for each station. However, due to computational constraints, we decided to develop a single global model instead. In future iteration of this work and with access to more computational resources, we hope we can reconsider the original approach as a potentially viable option for enhancing forecast. Additionally, future efforts could expand the available data by combining similar measurements from other geographical locations. Last but not least, our project also outlines the implication of forecast modeling and the data visualization in several areas. The first implication is proactive health alerts. Health agencies can issue timely alerts for vulnerable populations, such as the elderly, children, or people with asthma. The second implication should be infrastructure investment. Long-term pollution hotspots can lead to automatic infrastructure responses like traffic light changes or heating, ventilation, or air conditioning adjustment. The third, the third one will be for environmental monitoring and regulation. Forecasting visualization data support policy advocacy, planning discussion, and environmental assessment. The last implication, we think it should be the public interactive dashboard help the public understanding data, fostering greater environmental awareness and responsible behavior. That's all what our team has done. Thank you for listening.